Today's speakers are Matt Umberg and Ralph Rogers. Matt is an environmental engineer who has been with EPA since 2010. He has worked with drinking water utilities in the United States that perform online water quality monitoring in their source waters and distribution systems. Ralph is an engineering supervisor at the Philadelphia Water Department in the Bureau of Laboratory Services. He is responsible for the day-to-day operations of PWD's online water quality monitoring network.
Okay, thanks, Ashley. I'd like to start things off today by just giving a brief introduction to what we'll be talking about during today's presentation. So today we'll be talking about the use of online water quality monitoring instruments to produce real-time water quality data in a distribution system. And once real-time data is produced, that data is then transmitted from the field to a central location for analysis. And when we talk about these types of systems, we generally break the system design into 5 main design elements or aspects of the system design. And those design elements are shown on your screen. And they include monitoring locations, monitoring parameters, monitoring stations, information management and analysis, and investigation and response procedures. And each of these design elements will be addressed in the upcoming slides. The information from my portion of today's presentation is drawn from a guidance document that we recently published entitled Online Water Quality Monitoring in Distribution Systems. For the rest of this presentation, I will refer to this document simply as the guidance document. But if there are any topics that you would like more information on, feel free to come back and reference this document. It contains much more information and much more detailed information than I'll be able to cover during my portion of the presentation today. So before you even begin the design of a monitoring system, it can be helpful to complete a few activities ahead of time to help inform the design of the system. And the first such activity is to select design goals. Now, design goals are the specific benefits that you would hope to achieve through the deployment of a monitoring system. And through our work with drinking water utilities, we've generally found that most utility design goals fit under 2 main categories. The first category is the detection of contamination incidents, and this could include the detection of red water incidents, particulate matter incidents, and potentially intentional contamination incidents. The second main category is optimization of distribution system water quality. This can involve the management of chlorine residual, verification of effectiveness of both nitrification control and corrosion control, and also the tracking of water sources within a distribution system. I don't have the time to address each, really these examples in any detail today, but the guidance document breaks down each of these examples and goes into detail about types of monitoring locations and types of water quality parameters that can be helpful for achieving each of these examples. The second preparation step that can be helpful before design is to select performance objectives. Performance objectives are measurable indicators of how well a monitoring system achieves a utility's selected design goals. Shown on this screen are a few general examples, which include operational reliability, information reliability, and sustainability. And again, some more detailed examples are shown underneath each general heading shown on this screen. And then the final preparation activity that can be helpful is to review distribution system information sources. A number of examples of types of information sources are shown on this screen, broken down according to hydraulic resources and water quality resources. And basically, you can use these resources to accomplish a number of tasks. A few examples include you can use the information to identify areas of a distribution system that typically experience water quality issues. And that you could use that information to be able to select appropriate monitoring locations and parameters that can be monitored to achieve selected design goals. You could also use these resources to learn more about potential monitoring locations to inform the design of monitoring stations. And you can also use, say, historical water quality data from the system to develop a protocol for data analysis to help determine for a given monitoring location, what water quality conditions are actually anomalous and which conditions actually occur from time to time at that particular location. So now let's move on to the design of a monitoring system itself. First, we'll start with the first design element, monitoring locations. Now, for a given monitoring system, it would be ideal to produce data that would be representative of an entire distribution system. But oftentimes, budgetary constraints limit the number of stations that can be installed. So when we select locations, you should follow a strategic and methodological approach to select the locations to maximize the benefits of your eventual monitoring system. Through our work with utilities, we found that most utilities select the types of monitoring locations shown on this screen. And that includes distribution system entry points, operational control points, critical customers, interconnects, areas of concern, and mixing zones. Now, on this slide, once the potential monitoring locations are identified, it's often helpful to conduct an on-site analysis or on-site assessment of those locations to see if they would, in fact, work for station installation. The guidance document contains a template for a checklist that can be used for such an assessment. So this screenshot shown on the screen is just a part of that checklist that's available in the guidance document. This particular section breaks down factors related to the installation site. There are separate factors in the document relating to indoor installations and outdoor installations. So just in this, this portion addresses factors such as access restrictions, whether or not sufficient space is available for installation of a station, whether or not a location is subject to environmental conditions that could impact equipment that's installed, and whether or not a site is secure from tampering. Some resources that can be helpful for this design element include hydraulic and water quality models, such as EPA's EPANet. But just generally speaking, hydraulic and water quality models can be helpful to understand hydraulic connectivity between locations, can be used to determine travel time between locations, can be used to understand how water quality parameters change in the system, and also to predict water quality parameter values in a location. Another type of resource that can be helpful is, just generally speaking, sensor placement optimization tools. An example of such a tool is EPA's TIVA Spot. And these tools can be used they use a rigorous process for optimizing the placement of monitoring stations in a distribution system. One thing to note is that these optimization tools are based on hydraulic and water quality models, so accurate models are needed for the tools to be able to generate quality results and output. The second design element is water quality parameters. And through our work, we've found that there are four main, what we call core parameters that are helpful to monitor, and that includes chlorine residual, pH, specific conductance, and temperature. We found that these parameters are fundamental to the understanding of water chemistry and are useful to identifying a broad range of water quality changes that occur in a distribution system. But in addition to the core parameters, additional parameters, such as those shown on this screen, can be monitored and provide useful information to either meet utility-specific or site-specific design goals. These parameters can provide data that can supplement core parameter data to identify specific types of water quality changes in a given distribution system. The third design element is monitoring stations. Every monitoring station that's deployed should have 4 of the 5 functions shown on this screen. That includes power distribution, instrumentation, communications, and some sort of computing element. The 5th function on the screen, accessories. Accessories can be added to a base station design to either enhance the station functionality or to improve the station performance. And for each of these functions, the function should be designed depending on utility requirements and monitoring location conditions. Some resources that can be helpful for this design element include EPA's list of available online water quality monitoring instruments. And this is a product we just posted on our website that is a sortable spreadsheet for that lists available instruments that enables users to identify instruments of interest based on high-level instrument attributes and then be directed to manufacturer websites to learn more about the instruments and possibly obtain or purchase the instruments. A second resource is EPA's guidance for building online water quality monitoring stations, which provides information on how to design, fabricate, and install monitoring stations. And a third helpful resource is guidance for designing communication systems, which provides information for designing communication systems to transmit data from stations in the field to a central location for analysis. The fourth design element for these types of systems is information management and analysis. And I'll cover a few different aspects of this design element in the next few screens. The first aspect I'll cover is data validation. And data validation is the analysis of data to be able to identify inaccurate data so that it can be addressed so it would not intend or impact the intended use of the data or eventual analysis of that data. So if inaccurate values are detected, the data could be flagged, removed, or cleaned. And when you clean data, that basically means that you remove what you think is inaccurate data and automatically replace it with values that are likely to be more accurate. A number of different types of data can be used to validate the online water quality data. And those are the types of data are shown on this screen, and it can include water quality instrument fault indicators shown on the instrument themselves, communication system status indicators, station flow and pressure data, maintenance mode indicators, often shown on SCADA screens, and station environment information, again, often available on SCADA screens. Now, within the same design element, I'll address a few data analysis methods. The first method I'll cover is threshold analysis. And basically, threshold analysis is the establishment of threshold values for a given parameter that if the parameter data passes that data threshold, an automatic alert would be generated. So in the example on this screen, we see chlorine data, and we see a high threshold set. So once that chlorine data on the right side of the figure rises above the threshold, an alert's generated, signaling possibly the need for an investigation of a water quality incident. So you can have either high or low threshold values for this approach. You can also use an anomaly detection system. An anomaly detection system uses software-based algorithms that can enhance the behavior or can analyze the behavior of multiple parameters measured at a single location to identify anomalies. The screenshot shown on this page is taken from a screen within Canary, which is a type of anomaly detection system, and you can see the different analysis that is conducted on 4 different parameters for a given monitoring location. Now moving on from the analysis, another helpful aspect of information management analysis is data visualization. And a number of utilities bring their online data into their SCADA systems and are able to see time series plots. And that, in a number of cases, is great and satisfies the utility's needs. But if it's possible, it can be very helpful to develop a GIS-based data dashboard. And a dashboard is a visually oriented user interface that integrates and displays data from multiple data sources spatially and graphically. So in the example on this screen, we see the distribution system. We see the blue icons represent monitoring stations that are functioning properly. The red icons signify monitoring stations that are in a state of alert. We also see other types of data. We see locations in the system where customer complaint calls were made. So bringing in these different types of data types, we're able to, if there are clusters of different alarms or different types of alerts that are generated, you could be able to identify those quicker, seeing them spaced out on the map of your distribution system, and hopefully be able to respond in a timely manner. In terms of resources that can be helpful for this design element, first is EPA's exploratory analysis of time series water quality data. And this is a guidance document that provides information on analyzing time series water quality data to characterize normal variability and identify factors that impact water quality at a separate or at an individual monitoring location. A second resource is the Information Management Requirements Development Tool, which helps users define, consolidate, and prioritize requirements for information management systems that can be used for online water quality monitoring systems. A third resource that can be helpful is, we saw a screenshot of this before, is Canary. This is a type of anomaly detection system that was developed by EPA and Sandia National Laboratories. It is available for download and can be modified by users. And then a fourth helpful resource is the EPA's Water Quality Event Detection System Challenge, Methodology, and Findings, which is a report that summarizes an evaluation of anomaly detection systems that was previously conducted. And the fifth and final design element is alert investigation and response procedure. So an alert investigation procedure formalizes and standardizes investigations of distribution system water quality data. Go back real quick. So this is a template of an investigation process diagram. The guidance document contains this template that can be used to develop your own process diagram. So just looking at this closer, so basically a diagram like this should start at the point where a notification of an alert is received, progress through a process, an investigation process, and end at either a point where an explanation can be, for an alert can be identified to basically rule out contamination, or you progress all the way through the steps, get down to the bottom, say for this process, if activities are completed and contamination can't be ruled out, then theoretically you would have another process that you could advance on to be able to respond to a potential contamination incident. A helpful resource for these types of procedures is EPA's Exercise Development Toolbox, which can help users design, develop, conduct, and evaluate discussions and operations-based exercises. And these exercises can help to develop, teach, and improve procedures for drinking water utilities. So now we'll move on to the second part of today's presentation given by Ralph Rogers. Ralph, you should be good to go.
All right, thank you, Matt. Good to go. Good afternoon, everyone. I want to thank you today for joining our webinar, and I also want to thank EPA for giving Philadelphia Water the opportunity to showcase our efforts with regard to online water quality monitoring. My presentation is going to focus on 4 areas. I'm not going to go into the weeds too much. We just don't have enough time. Just going to give you an overview of what we've done. So these 4 areas that we're going to briefly cover are an overview of our system, how we incorporated online water quality monitoring into surveillance and response, go through a little bit about our level of effort for online water quality monitoring, our instruments, the station design, and so forth. And we're going to wrap up with some of the support requirements that we had to implement in order to operate our system. Next slide. Here we go. So Philadelphia Water Department is a surface water utility. The map on the right shows the Delaware River on the far right and the Schuylkill River in the center. Our customer service base, we have approximately 1.6 million people, 134 square mile service area, and approximately 460,000 residential accounts. Our finished water, we have approximately 400 million gallons of finished storage, and our daily production is anywhere from 200 to 225 million gallons of daily production. The characteristics of our distribution system, we have roughly 13 pressure zones, 3,200 miles of water main, 90,900 valves, and 25,300 hydrants. What you can see on the map is that we also have 3 main water treatment plants. The blue area is our Baxter Water Treatment Plant, which is our largest. And to the left in the purple is our Queen Lane, and lower left is our Belmont, which both draw off the Schuylkill River. And in the far lower right corner of the map in the green area, that is a part of our distribution system where we have mixing that occurs. So online water quality monitoring is a major component for a surveillance response system. Online water quality monitoring is the beginning of the SRS. That's where all the data is originating. Our system consists of 42 fixed monitoring stations, and we also have 8 portable units, which we refer to as rapid deployment modules, and I'll discuss them a little bit further. We have complete coverage in all our pressure districts and all our plant service areas. Key infrastructure is treatment plant effluents, our pump stations, storage tanks, reservoirs, and distribution sites. And these are key when you're developing your site selection because it's a lot easier to just skeletonize your system and start out with sites that you already have, that you already are operating. This provides real-time event detection. We have continuous data flowing, 2-minute polling rates, and in addition, we have our routine sampling program, which consists of about 80-plus sampling sites, and some of those sites are grab samples are collected daily. So in addition to the key infrastructure locations, we also sort of superimposed our additional OWQM sites based on our routine sampling sites. So we could do comparative analysis of what the sensor data is reading and compare it to laboratory analysis of the grab sample data. So an overview of our OWQM system. As I said, we have approximately 42 sites fixed, spatially distributed. Each data point, each dot is a representative of a OWQM site. In addition, we have the 8 what we call rapid deployment units, and these are very helpful for water quality investigations. As we see anomalies in the system, we can get confirmation that an event is occurring as opposed to running out and trying to grab a grab sample. It's also helpful for customer complaint support. Oftentimes, a customer calls in a complaint. You send a response team out, and the plug of water is already passed. So we have the ability to install these units 24 hours a day so we can see what's going on. It's also helpful for new site selection when you're considering putting in an additional fixed monitoring station. You want to make sure you have variability at that node so you can actually see. It's a huge level of effort to put in a station. So if you could do some sort of reconnaissance in advance, it's very helpful. In addition, we also use these units for special events monitoring. Philadelphia has hosted some large venues, activities over the past, the Pope's visit, the NFL draft, the Democratic convention. So we deploy these units in strategic areas. So there is a water security component, an application that we use these for. We also, as I mentioned in the previous slide, we have all of our infrastructure covered for OWQM monitoring. In addition to city-owned facilities, the police and fire stations, Philadelphia International Airport, and private stakeholders. It's extremely important to develop these collaborative relationships with private stakeholders because not every part of your distribution system is a city-owned or utility-owned location. Now we're going to get into the surveillance and response. As Matt mentioned in his presentation, there are 2 main reasons why you develop an SRS. PWD follows that same protocol. One is detection of contaminant incidents, and the primary concerns are both intentional and unintentional contamination. Not every incident is intentional. There could be backflow situations, mechanical failure in the building premise plumbing that causes the backflow, or a water main break. So it's important to be able to see what's going on and detect these as quickly as possible. Also, to optimize distribution system water quality. Data is used to establish baseline water quality conditions to ensure that water quality parameters are in acceptable ranges. I want to take a minute to point out that from my experiences with online water quality monitoring, you're never fully optimizing because the technology is constantly changing. There's always a new sensor. The precision and accuracy is getting better. So it's a sort of a moving target. It's always kind of moving. Also, it could take years to establish baseline water quality conditions because Philadelphia, where we're geographically situated, we have seasonal variations. So we go through all 4 seasons. So as the water temperature changes, operations change, our baseline is constantly changing. So it takes a while to really establish that baseline water quality. This slide, I'm not going to go through the entire slide because the purpose of my presentation is to focus mainly on how we implemented monitoring. The far right of the slide, the data analytics and the response, there just isn't enough time to get into that in greater detail. However, on the front end, I want to point out that developing the protocol for your data and communications should really be established at this point on the front end, because at the point of data transfer, when it's going from the online system into the event detection system or the water data management system, having the data protocol established on the front end really drives downstream software and hardware requirements. And so you don't want to constantly be changing your protocol. For example, industry standard is Modbus. We started out using Modbus. We now have migrated into DMP3 protocol, which really allows us to mitigate any communications loss and data loss. Our data transfer, we're using 3G, and we're migrating to 4G cellular systems. And so everything, and I'll show you in a future slide the actual architecture. So I don't want to spend too much time on that now, but the goals of your SRS, it's important that you really focus on the dual use benefits, not just for learning what's going on in your system and reapplying, but just want to throw this out there for budget and for funding requirements. If you are able to show your commissioners and your water boards that, hey, we're really going to maximize the benefits of implementing a system, it would be a lot easier to justify getting funding for your system. So how do we use it? We use it to develop a better understanding of our distribution system. We're learning water quality trends. We're looking at how pumping rates and tank operations affect our chlorine die-off and potential nitrification in storage tanks. We're looking at how mixing in the lower parts of our distribution system are affecting water quality. In addition, we're providing support to the surveillance and response system. It's not just the Bureau of Laboratory Services that's looking at this data. We're partnering with other interagency partners, such as our conveyance and load control, our public health department, our GIS group. So all this information is going into the dashboard, and it really helps us learn what's really going on, how other operations within our utility could potentially affect water quality. And most importantly, one of the biggest benefits from my end, because I'm the systems integration guy, is by having an open architecture and when you're developing your hardware and software on the front end of the project, maintaining this open architecture really allows you to integrate new technologies much more easier. And the data analysis also, the data management group constantly provides me feedback so that I can develop my maintenance procedures to improve the sensor performance and get better quality data. This is just a very generic sample of what a dashboard looks like. We have a grab sample site. We have your GIS interface. You have and this is an actual screenshot from one of our OWQM sites. So you have the drop-down menu. You can see in real time what's going on for the parameters. And then any customer complaint response. All this information is being fed into the dashboard. So you can see what's going on so you can make that determination of if an event's occurring. So now we're going to run through the components of our system. So I think this is just a repeat of an earlier slide just to kind of refresh everyone's memory of what our sites are, how they're located, and so forth and so on. One thing I want to point out on this time, however, is with our private stakeholders. What we have found that with some of our private stakeholders, it has allowed us sort of to delve into the premise plumbing monitoring, and also allow some of our stakeholders who have partnerships with Homeland Security, we're able to provide them water quality data reports that they can then feed or provide to Homeland Security so that they get additional funding. So it's sort of, we want to really maintain those win-win relationships with our private stakeholders. Let me see, slides are all slides. So at the station level, Matt mentioned earlier about some core parameters. We've kind of expanded on that because we're not just doing water quality monitoring, we're doing water security as well. And I'm not giving you all the information here. This is just some very basic parameters that we're using. So we have total chlorine. We're using both primary and redundant sensors. So we're always getting a disinfectant residual level back into our system. We have our conductivity because we have multiple sources. We have mixing zones. Turbidity, pH. We have oxidation reduction potential. That's basically a heartbeat. That's telling us that, okay, our system is operating. There's no foreign substances that have been introduced into the system. So that's a parameter that should always be flatlined. If we see a change in that, we know something's in the water that shouldn't be there. Of course, temperature, we use 254 or UV 254 as a surrogate for TOC. We also have sample pressure, and we have flow switches at our stations. We're not monitoring the flow, the amount of flow. We're just making sure that we have a flow indicator. Our communication system is a 3G wireless cellular network, and we also have, we're constructing or building a 4G wireless network for redundancy. Early on in our system, we had cellular and radio, spread spectrum radio, but we migrated away from unlicensed radio, and we're replacing that with a 4G network. The alarms that we have coming in are our water quality alarms for each parameter listed above, and we also have intrusion alarms for our enclosures themselves, not the physical structure of the building, but just the enclosures themselves. We have communication failures alarms, and we have power failure, and I know that they're beyond the UPS back. So if we have a power failure, we do have backup batteries on site, so we won't know immediately that there's a power failure until the UPS runs out. That's a systems integration thing that we're trying to address. And we also have alarm-triggered automated sampling features. That kind of falls into that accessories block that Matt mentioned. So we could trigger a sample 24 hours a day at most of all of our locations, all of our stations. Not all of our stations are outfitted with automated sampling. That's a work in progress. This is a sort of an overview of our data communications network. It's sort of a generic version for security reasons. I didn't list everything, but essentially the layout is on the left we have a typical fixed monitoring station. On the lower left is our rapid deployment. Rapid deployment modules are outfitted with 3G modems, so we can deploy them anywhere in the city and link into our system. So data is transmitted from the remote locations into our OWQM clear SCADA system is what we're using. That's the DMP3 protocol. From there it goes in, and we also have a redundant server. So data is actually being transmitted to both servers simultaneously, but only one server is acting as a primary. So there's a link between the two servers so that each server knows which one's the primary. If they don't have that heartbeat between them, they just automatically take over as the primary. All the data then comes in. I don't know if you can see me moving my cursor or not, but this little blue circle on the far right, that's representative of that data transfer link I mentioned earlier. And all those little lines are representative of all the other components of our SRS that are feeding into that dashboard. And then the lower left is just a spatial, just kind of give you a geographic representation. So each one of those dots is a monitoring station. Each station's providing 2-minute data, and I believe it takes roughly 5 minutes for each station to report. So, but the data is stored on site, and once it's called up from the main server, it just transfers all that data. So the next slide, we're going to go a little bit deeper. We're going to go to the local level. This is what the sort of components of our sites look like. On the far left, we have our sensors. That's all fed into, that's sort of that computing component that Matt mentioned. Everything goes into an RTU. That's our I/O. Then from there, it's going into the wireless modem. But up in the above the RTU, I have what we call an operator interface. And for the instrument guys out there, that is I can't tell you how valuable that having an interface on site is. Essentially, that's taking the computer from the remote location or from my office and putting it on site. So it allows my technicians and engineers to see the data as it's being transmitted, so they know that the value going into that RTU is the value that is being transmitted, and it's a very helpful feature. On the lower left is a typical auto sampler, and again, this just shows you the primary and redundant servers that the data is being transmitted to. Let's see, I think I'm doing good for time. So this, I'm going to go through just some designs. Philadelphia, because we're such a large city and because we have a diverse array of buildings and structures, there is no one-size-fits-all. And the takeaway from this is that there is no one-size-fits-all station design. In this particular design, this is one of our private stakeholder locations, which was very deep into the basement, and we literally had to carry every single component into the basement and assemble it in place. So it allows us that flexibility to do different things. And this is an earlier design. We're in the process of upgrading our designs. We've gone through several design iterations over the years. This is a standalone. This is for those locations where you just cannot get into the building. It's just physically impossible to get into the building, but you are able to access the main. So you just run a service line from the main to the, hopefully a secure location or in the perimeter of the building, and hopefully you have a very positive relationship with the stakeholder that allows you access. This is one of our older standalone designs. We've, again, have since upgraded these designs to incorporate more functionality, add more water security parameters to it. But this isn't a huge level of effort for these types of designs, but we did not fabricate these. We actually outsourced them to have them fabricated, but all the designs were done in-house and in collaboration with our systems integrator. And this is one of the first generations of our what we call our rapid deployment module. Again, this is an older design. We've since redesigned this twice. The next generation that we're working on will incorporate automated sampling. So we kind of figured, hey, we have enough experience with online monitoring. We're deploying these units. If we do see something and we're detecting something, it'd be great to have a sample. So we're working on developing a 1 or 2 liter sample bottle that could be integrated into this design. So I'm a little bit ahead of schedule, but I'm going to kind of go through some of the system support requirements. I just want to say, before I begin this, these are for Philadelphia Water Department, our design. So if you're a small or medium-sized utility, you might not require this level of support, but the QA/QC requirements should definitely be similar. The staffing requirements could be adjusted a little bit, but the QA/QC measures that we have in place, we developed an online water quality monitoring SOP and also a QAP, which is a quality assurance project plan. The SOP includes all our project documentation and policies. It also includes troubleshooting and repair procedures, not only for the instrument technicians, but also for the engineering staff. So we have flow charts where the instrument tech can follow the sequence through the flow chart, and then he gets to a point where it's okay, I need to get an engineer involved, and that's where their responsibility ends, and the field engineer has to come in and take over from there. We also developed in-house video SOPs because we have engineering interns that cycle every 6 months, and we found that it's a lot easier to have video SOPs where they can just sit down and see the procedures before we actually take them out in the field. We've also used these SOPs for PAWWA training sessions as well. So it just makes it a lot easier because you don't want to give somebody a 200-page SOP and expect them to read it in 2 days and know everything. So some people are more visual. They like to see things before they actually go out and do it. The SOP covers the daily, on the right side of the screen, it kind of shows the daily O&M, the preventive maintenance and alarm response protocols. So the SOP covers the daily sensor review and alarm response. We do a daily review of the network, identify alarms, everything's prioritized, which alarms get more priority than others. They go through weekly QA checks. We do a check on every single station every week. We do a monthly sensor performance check, which is a little more advanced. We use buffers, reagents, and every single station, every sensor gets calibrated every 3 months regardless, and that's merely to preserve the integrity of the data. So there's a lot of effort involved in what we're doing here. The next slide is sort of open. This is what we have in effect at PWD. We break our system up. We have the instrumentation side, which is my responsibility, and then we have the data side, and that's where the demarcation is. As you can see, there's a lot of people involved, a lot of staff. On the instrumentation side, we have one program manager, myself. I have 2 engineers. One engineer focuses on field operations. The other engineer focuses on systems integration. So that engineer is sort of the liaison between the instrumentation and the data side. I have 2 instrument technicians, and then I have 2 engineering interns. For systems integration support, we have an engineering consultant that helps us, and we also have internal PWD and city IT resources. On the data side, there's a program manager, there's 1 engineering supervisor, 2 full-time equivalent engineers that just do data review, 1 full-time engineer that just does event detection, and an engineering intern that sort of reviews the grab sample data versus the sensor data and sort of does these sort of precision and accuracy calculations to see what the sensor performances are. They also have their IT support, which consists of PWD developers, PWD network, and they also have their own IT consultant as well. That pretty much concludes the overview of PWD. Now, if anyone has any questions, we could open the floor up to questions. If someone wants me to elaborate more on a particular slide, I think we have some time to do that.
Real quick, Rob, can you hand control back to me real quick?
Sure. Let me grab the ball here. The green ball is on you.
Yep. That's good. Yep.
Got it.
So just to wrap things up, thank you, Ralph. If you would like more information, feel free to visit our website on online water quality monitoring, shown on this slide. It contains many of the resources that I referenced in my part of the presentation today. You'll notice that the second item in the main column of documents is the main online water quality monitoring and distribution system document. The first item is an equivalent document for online source water monitoring, if you'd be interested in that. In the box out to the right is the list of available online water quality monitoring instruments, and there are additional documents if you scroll down on the screen. So please feel free to visit that website for more information and materials. If you have any questions at all or just would like to discuss online water quality monitoring and distribution systems, I'm sure with me and I'm sure Ralph would be willing to talk, but feel free to reach out to us. Also, if you are from a utility and your utility currently does online water quality monitoring, either in its source water or distribution system, please contact me. We have a great group of utilities that helps with the sharing of information amongst the group of utilities to help each individual utility maximize the benefit of their systems. As far as our next webinar in this series on water quality surveillance and response systems, next webinar will cover communication systems for smart utility infrastructure. It'll be on July 17th from 1 to 2 p.m. There's a link on this page to directly register for that webinar, and the link at the bottom of the page, the very bottom, you can click on that link for the full webinar schedule and to see recordings of previous webinars. I'd expect the recording of this webinar to be available maybe within the next couple weeks or so. So now if we could upload the questions, the poll questions are uploaded, so please respond to the poll question on your screen. And Ashley, if you could let us know if there are any questions.
Sure. So far we have a few questions. So the first one is, cell communications are notorious for unreliability during significant emergencies. How would this impact PWD's systems to be responsive during emergencies?
I guess that question's for me, right? Well, right now, early on in our project development, as I mentioned, we used to have spread spectrum radio, and so during that era, we experienced quite a few communications losses, and we were using Modbus protocol initially, and the Modbus protocol did not allow for immediate repopulating of the database. And that's why we migrated into DMP3, because at least if we lost communications, we knew we would recover the data. Since we've migrated into 3G and we're in the process of actually going to 4G, we really, the loss of communications hasn't caused a major issue with data loss. And we've only lost communications at certain stations, so we haven't had a network-wide communications loss, fortunately, and that's the reason why we are building in redundancy for that reason. So it's important to not just rely on one single mode of communications. You should consider, once you get through your proof of concept and you get a few sites up and running, you really want to consider having redundant communications sources. So, okay. Thanks.
All right, thanks for that. And then the next question is, how often are your detection systems pulling samples?
The data is being pulled continuously, but we're on 2-minute polling rates. So we could go more, like we could get closer to 1 minute, but then it kind of gets a little noisy, and on the back end of the project with the event detection, it kind of causes problems with the event detection because there's sort of a conflict sometimes between the OWQM's system and the event detection. So, but 2 minutes is pretty much the standard polling rate.
All right, and then the next one, I'm not sure of the context. It says, what benefits have PWD observed? Have they detected any incidents of abnormal data?
Unfortunately, I'm not on the data management side of things, so I can't go into specific incidents of data and how the data has been utilized. As far as benefits, it's one of the biggest benefits that I've noticed is that our pumping unit and our load control units have gained a better understanding on how their operations affect water quality. And in fact, over the years, they've become proactive and have even reached out to us to let us know, hey, we're observing something going on at one of your monitoring locations. Are you aware of it? So it took some time to change the culture within the department. So I think that was one of the biggest benefits, just getting everyone to realize that, hey, this is a useful tool to help them with their jobs. So, but it takes time to change that culture within a particular utility, especially a large utility like PWD. But it's been a positive impact for sure.
We have 2 questions left, and then we're getting close to the top of the hour. The next question is, sounds like at PWD, comparisons between OWQM results and regular sampling results are made. Are water quality regulators, such as EPA, state primacy agencies, or other agencies, typically involved in deployment of OWQM systems? Can OWQM results be used to replace real compliant sampling or otherwise support water system permit compliance?
That's a lot of questions. First off, the regulators are not involved with the selection of online water quality monitoring locations. As far as grab sampling locations, that's not my area. I can't speak to that. But I believe the latter end of the question was sort of addressing whether or not online water quality monitoring could be used to replace grab sampling. That's a big question that's been floating out there, and in my professional opinion, the sensor technology is just not there to replace laboratory methods. A lot of the laboratory methods are approved by EPA, and that data is reportable for compliance reporting requirements. Online water quality monitoring in the distribution system doesn't have those reporting requirements yet, and I know that some of the smaller utilities, for financial and budget reasons, would like to use a sensor to replace grab sampling, but I just don't think the technology is there yet, in my opinion, because there's just, as you can see, the level of effort that we have just going through the data management and detecting false positives and is it a real event. So you just can't put a sensor in and walk away and say, okay, I'm going to use that value. It's a very complex question to answer.
So we have another 6 questions. It looks like more folks asked questions after the last round. Do we want to stay online to respond to these questions, Matt and Ralph?
I don't have a problem with that.
Yeah, that's fine. It's fine with me.
Okay, great.
So if you just really quickly, if you don't hear the answer to your question or would like to check back, first of all, if it's your question, you can email either Ralph or I, and we will get back to you. If you just would like to follow up, check back within the next couple of weeks or so for the video of this presentation and just go to the back of the recording to try to find the answer to questions.
All right. So the next question is, have PWD or any other utilities detected an act of intentional or other significant contamination that wouldn't have otherwise been detected by using an OWQM system?
I will tell you that no utility will respond to that question for water security reasons. Whether it's if it's an intentional incident, most utilities will not respond to that question, and I am not authorized to even address that. So sorry to kind of seem like I'm evading the question, but that's sort of the policy that most utilities have. They won't speak to that.
All right, so moving to the next question. Using ATI monitors, do you have a problem with readings floating during water temperature changes?
I'm sorry, could you repeat that?
Using ATI monitors, I don't know if that's the right reference. Do you have a problem with readings floating during water temperature changes? Maybe fluctuating?
I'm not sure what you're asking. I mean, it depends on the parameter. You know, so if it's a specific parameter they're interested in, we have seen some variability when I'm assuming the question is referred to mainly like seasonal changes when you're going from winter to summer. Most sensors respond differently, perform better in warmer temperatures than they do in colder temperatures. We don't see any major differences because we do a lot of sample conditioning, and there's a lot of things that I didn't cover in the presentation. So every instrument, no matter what it is going to require some sample conditioning beyond what the manufacturer is recommending because it's going to be specific to your water utility.
All right, thanks, Ralph. The next question is, what make and model of remote analyzer do you use?
Generally, overall, we're using, for our core parameters, we're using ATI instruments. For our UV254, we're using Realtek instruments. Those are our two primary manufacturers that we're using. I mean, we're using different manufacturers for different, like for pressure and flow and things like that. For our hardware, we're using different manufacturers, but primarily the sensors are Realtek and ATI.
Okay, thanks. The next question, what kind of platform do you use to interface GIS data with SCADA, and what SCADA systems do you use?
As far as GIS, that's further down the data streams, more on the dashboard side. The SCADA software that we're using is called Clear SCADA. It's manufactured by Schneider Electric, and that's the DMP3-based protocol that we're using. And that's our primary system. That's why I said it's important to develop your protocols on the front end, because when you get further down the data stream, that's where all the different software and interfaces come into play. So I kept it as simple as I possibly could, maintaining that open architecture.
All right, so this next question is a two-part question. The second part I'm not quite sure on. I don't know if it'll make more sense to you. Are some instruments backed by the UPS as well as the RTU? If so, which have you found beneficial to battery back?
The instruments are not backed up by the RTU. In fact, everything is backed up by UPS. So all the instruments are, in our situation, we're all loop power, 24-volt DC. Everything comes off of a 24-volt DC power supply. The RTU is also 24-volt DC, so and all that is fed off of UPS. So there aren't separate battery backups. The only battery backup is the UPS that is backing up everything, the RTU and the instrumentation.
All right, and then our final question, has PWD seen any explicit reductions in operating expenses, for example, labor or time associated with manual grab sampling, as a result of the deployment of OWQM instrumentation on the network?
No. We have our grab samples are regulatory compliant for our permitting and so forth. So the online water quality monitoring network was not developed to eliminate grab sample locations or the number of grab samples. But what we have seen is a reduction in operations and maintenance costs of the OWQM by utilizing streamlined QA/QC procedures and looking at emerging technologies and incorporating new technologies. So on the back end, again, each utility is going to be unique, but for our purpose, it was never our intent to replace grab sampling with online water quality monitoring. It was online water quality monitoring is being used to enhance that program. That's it for me. Any more questions? Thank you.
We haven't gotten any additional questions in, so we are all set there.
Okay. Well, thank you to Ralph and Ashley, and thank you, everybody, for attending today. Have a great day.
All right, Matt. Thank you very much.
Thanks, everybody.